Okay, picking up where we left off in the previous video, you can see where in the problem you get the equation y equals a plus bx, in this case x being t, and you'd get 0.57 rounded to 2 decimal places for a and 0.069 rounded to 3 decimal places for b. Does it really matter how many decimal places? Not really that much here. Alright, then what does this linear regression or this line of best fit tell us? Also called the least squares regression line. Well, I could have used just as I did at the bottom of the screen there, I could have used those numbers to construct a function for p, plug in t is equal to 45, and get a value for the price of milk, the estimated price of milk in 2005, which is now a long time ago. I can also do something else, so let me step you through this extra feature here as well. I go back to my calculator. Let's run through it one more time. We're going to go to Stat, to Calc. We're going to go down to LinReg, which stands for Linear Regression, number 8. I'm going to put in my two lists, which is list 1, comma, list 2, comma, and this time I'm going to supply a place where I want to store the function that this creates, or the equation. So I'm going to go to variables, then to y variables, to function, to y1. And so what that's going to do when this is done, it's actually going to create a linear equation and put it out in my y1 variable. So I'm going to run this now, and I get the same thing that I got before. By the way, those two numbers, r squared and r at the bottom, r squared is what we would call the goodness of fit. It tells us how well our model, this linear model, models the actual data, or how accurate it is in modeling the actual data. And it's 0.98, which means it's a fairly good, it's 98% accurate in a manner of speaking. The r at the bottom is the coefficient of correlation, and that measures how tightly the data are fit around the line. Anyway, those are two extra things from statistics. If I went back again to now graph my function, you will not only see the data points that I put out there, but you'll also see the line of best fit. And since we are looking for the value in 2005, which would have been 45 years, we can, at this point, go to Second, Calc, look for value, and I'm going to put in when x, or x is representing t here, out to there, and it tells me then that the value in 2005, or 45 years after 1960, should be this value down here, 3.659. 3.659, which would be $3.66, which is a slight bit off, and the reason is because I have a lot more precision in my numbers. Once again, if I go into y equals, you can see that I not only have 0.57, I have 0.566, 44444, etc. And the same thing will hold true with the digits on the B part. So you can see how many digits it really stores out there. 0.6873333, etc. Now, I mean, this is important. If you were doing this, you can see that 2 cents is not really that far off, but yet losing those decimal places of precision is enough to cause a 2-cent difference in the final calculation. So, which is more accurate? Our model is actually more accurate, but it can be rounded, and it's for the sake of this particular problem, it was easier to calculate with only 2 decimal or 3 decimal places. So I hope that makes sense and you get a feel for what you can do with the calculator in statistics.